Where were we? Last time, we talked about recursion, which is very similar to induction that we had talked about the previous time. And today, we're going to be doing something very similar, but with a more computer science sort of feel to it. So in particular, we're talking about recursive algorithms. So it should be a little bit familiar, and many of the things will be things that we've talked about over the past couple of days and even before that. But we're going to approach it from a slightly different point of view, which, as I said, is a little bit more computer sciencey. So we're going to be talking about algorithms and talking about their complexity. Well, let's start from the beginning. So a recursive algorithm, this is not going to be anything particularly new, but let me just write it down. A recursive algorithm solves a problem by reducing it to a problem, sort of the same problem, but with a smaller input. So there's going to be a little bit of getting used to if you have not seen any coding before. I'm going to try not to assume that you're too familiar with it, but we're going to work a little bit informally as well. So hopefully you can pick it up. But let's do an example to start fixing these ideas. So for example, a recursive algorithm to compute n factorial. So this is the factorial exclamation point. And just in case you don't know what that is, n factorial is equal to n times n minus 1 times n minus 2 times 2 times 1. So it's just multiplying all the numbers from 1 to n. And so let's write this down. We will call it factorial, and it will take an input n, which is an integer at least 1. You can talk about 0 factorial, but I'm going to skip over that because it's not particularly relevant to this context. Okay, so we're going to write down a little algorithm, and we're going to write it down in pseudocode, which means it's going to look like code in the sort of formatting and style, but it's not going to be actual code. So here's our little algorithm. What it does is first, we check if n is equal to 1, and if it is, then we return 1. So this we should think of as our base case. 1 factorial is 1. And then otherwise, we will return n times the same algorithm applied to the input n minus 1. So this is the recursive step, or let me just say the recursion, which is using the fact that n factorial is equal to n times n minus 1 factorial. You can see that pretty immediately from this formula up here. If it's not already obvious, let me make this n prettier. Right, because n factorial is n times this whole thing is n minus 1 factorial. That's all this is saying. So let me make some comments for anyone who is not very familiar with coding. So this is what I mean by pseudocode, where this is not written in any programming language, but it is written in the style of code where we have certain commands on certain different lines, and we say things like, if we check this condition, then we do that, and otherwise, which we write as else, we return something else. And I should say that return, for anyone who's unfamiliar with this kind of stuff, means this is the output. So an algorithm has an input and an output. And in this algorithm we've written down, the input is n, and the output is whatever ends up getting returned. So it can either be this, or, so we have two return statements, could also be this. But you should be able to see from the structure of this algorithm, only one of these things will end up getting returned. So you're going to only have one output, like you expect. So to be concrete, let's sort of track down what happens when we apply this algorithm. So what happens if we run factorial of 3? So let's just go through this program. If 3 is equal to 1, well, it is not. So we will skip the rest of that step. And instead, we will do the other thing, which is to return 3 times factorial of 2. So this is going to be our output, but in order to figure out what that is, we are going to have to run this factorial again. And so this is the recursion. We're running this factorial algorithm, and as a step in the algorithm, we run it again on a different input. So let's do this. Now we have factorial of 2. And the point with recursion is that our new input is smaller than our initial input. So if we keep doing this process, after a certain number of times, we're going to get down to our base case, and that's when it will finish. So factorial 2 says, if 2 is equal to 1, which again, it is not, so we do the other thing, which is to return 2 times factorial of 1. And here we get another recursion, factorial of 1, if 1 equals 1, which it does. So we've made it to the base case, and the way this program works now is that we return 1, and that finishes this program, so we don't make it to the next step. So when you return, it finishes there, and that is the output. So the output of this recursion is 1. The output of this recursion is now 2 times 1. So this output is 2, and then here we finally get 3 times 2. So the final output is 6. So I hope this diagram is a little bit helpful for understanding how recursion works. You can sort of follow the arrows through the whole process, where you start with this function call, applying this function, and then you follow the arrows down through these recursive steps until you finally reach the base case at the end, and then you come back up to get the output. So somehow when you're doing a recursive algorithm, there's sort of a downward step where you are recursively calling the function. And then there's an upward step where your function is returning outputs and you are building up those outputs into the solution. So this is essentially how this algorithm works. And now I want to introduce an important idea about understanding algorithms, which is their complexity. So the time complexity of an algorithm what is this? It's somehow is measuring how long the algorithm takes to run. So how much time it takes. And the way you measure this is you look at how many sort of basic operations the algorithm uses. Oh, this mic is on. I hope that is not on accident. Okay, so it's a number, it's a count of the number of basic operations the algorithm uses to find the solution as a function of the size of the input. So this might be, if you haven't seen it before, a little bit to swallow, but let's look at this example we just did and go through it to figure out what this means. So, so in factorial 3, we used, so what are the kind of basic operations we're talking about? We're talking about things like comparisons, additions, multiplications, basic operations like that. So here is a comparison, and here is a multiplication, and here is another comparison and another multiplication, and here is another comparison. So this algorithm used 3 comparisons and 2 multiplications. And if you look at how this pattern goes, so each time you call the function, it's going to have 1 comparison and 1 multiplication, unless it's the last one. And if you plug in some number n, this would use, basically, if you think about that pattern, it will use n comparisons and n minus 1 multiplications. For a total of 2n minus 1 basic operations. But the way we normally think about this is we don't need to worry about the exact formula, and we don't really worry about the difference between comparisons and multiplications. Usually what we do is we just collect it all into this big O notation. So in particular, we forget the constants and the operations, and say that it's O of n. So this is said big O of n, or just O of n. And what this means is that the number of operations is no more than some constant times n, where n is the input. So this kind of thing we call linear time, because function n is a linear function. And basically, since we're forgetting the constants, we're sort of using this to mean any multiple of n, so any linear function, which is why we call this linear time.